Welcome, everyone, to Gradient Daily. I'm absolutely thrilled you're here with us because today we are unpacking a true paradigm shift in the world of generative AI. Today's explainer is a deep dive into a fascinating new paper titled DomainShuttle, Freeform Open Domain Subject-Driven Text-to-Video Generation. This groundbreaking research comes to us directly from the brilliant minds at the Hong Kong University of Science and Technology, working alongside the Creative, Controllable, and Cognitive Computing Group, often referred to as C4G. Now, if you've been following the AI video generation space for a while, you probably know we've gotten pretty darn good at what we call in-domain subject preservation. You know the drill. You give the AI a picture of your dog sitting on the couch, and it can generate highly realistic video of your dog sitting on that exact same couch. It works great. But the very second you ask the AI to put your real-world dog into, say, a beautiful watercolor painting or maybe a 3D animated cyberpunk city, the models just completely break down. They either lose the subject's identity entirely or they completely fail to adopt that new visual style. Well, this paper fundamentally solves that problem. DomainShuttle introduces a truly revolutionary step in subject-driven text-to-video generation. It moves us away from those simple, rigid copy-paste mechanisms and introduces a framework that genuinely understands semantic decoupling, giving us unprecedented control over visual style. We are going to treat this explainer as a graduate-level lecture because to really appreciate the magnitude of what HKUST has engineered here, we have to look closely under the hood. So get comfortable and let's dive into this.
Here's our syllabus for today's deep dive. We're going to start by defining the open domain S2V problem, then we'll move into Domain-MoT and feature decoupling. After that, we'll unpack DualRoPE spatial disentanglement, break down the cross-pair consistent loss formula, look closely at their datasets, and finally wrap up with a critical discussion of the results.
All right, Section 1, the open domain S2V problem and its core limitations.
To truly appreciate the elegance of DomainShuttle's solution, we first need to intimately understand the problem they were up against. The inciting incident for this entire explainer is a fundamental, almost structural flaw in our current video foundation models. Think about subject-driven text-to-video, or S2V. It has incredible real-world applications in advertising, creative design, and especially AI filmmaking. But right now, S2V is effectively trapped inside a stylistic box. Current models excel at copy-pasting and identity, sure, but they fail miserably at true, flexible adaptation. They memorize the exact pixels of your reference image, and because they memorize the pixels, they memorize the lighting, the background, and the specific visual style of that reference. So when you try to prompt the model to generate a video in a totally new visual style, say taking a standard photograph and prompting for a low-poly 3D video, the model faces an impossible contradiction. It literally tries to force realistic photo pixels into a 3D stylized environment, and the result is a chaotic, unusable mess. And this image brilliantly illustrates that exact contradiction. I want us to spend a good amount of time analyzing this visual grid because, honestly, it tells the whole story. If you look on the left side, under In Domain, we see what existing S2V methods actually do quite well. Look at that multi-object panel. You give the model an image of a dog and a red pillow, and it successfully generates a smooth video of that dog and pillow on a couch. The environment and the visual style completely match the reference image. The model is basically doing advanced, localized copy-pasting. But now I want you to look over at the top right, under Cross-Domain, specifically looking at that real to fantastic scenario. In the top row, the reference images are photographs of a real man and a real woman. The prompt asks for them to be placed in an animated, highly stylized world. The existing methods, which are marked by that sad face icon, fail catastrophically. There's no other way to say it. The identities bleed together, the requested visual style is completely lost, and the output looks like a distorted, frankly terrifying blend of real human and cartoon faces. The model just couldn't separate the identity of the people from the photographic style of the reference image. Now look directly below that massive failure. That is DomainShuttle's result. The man and women are seamlessly translated into a beautiful, consistent 3D animated visual style, yet their core facial features, their intrinsic identities, are perfectly, flawlessly preserved. And the exact same thing goes for the fantastic to real scenario at the bottom right, taking a 2D cartoon fox and rendering it as a highly detailed, photorealistic painting on a wall. DomainShuttle achieves a level of generative flexibility and aesthetic control that prior models simply cannot touch. So how exactly do they do this? Well, it all starts with their first major architectural breakthrough. That brings us to Section 2, Domain Motif and Feature Decoupling.
The researchers at HKST realized something crucial. To achieve the stunning visual style translations we just saw, you have to fundamentally change how the neural network actually processes information. The core philosophy here is that video features must be decoupled from reference features. You simply cannot process the target video and the reference image through the exact same attention pathways and expect the model to somehow magically figure out what part of the image is the identity and what part is just the style. You have to force that disentanglement architecturally.
To really ground this incredibly complex theory, I want to use a concrete, everyday analogy. I want you to think of a multilingual translator. Imagine you have this beautifully written story in French. The story has a very specific plot. It has certain characters and a core underlying meaning. For our purposes, this meaning is the intrinsic identity of our subject. Think of it as the bone structure of a face or the specific physical markings on an object. Now you want to translate this story into Japanese, which represents our target domain or our new target visual style. If you use a poor, inexperienced translator, they might try to translate the French idioms literally, word for word, into Japanese. The result? Sentences that make absolutely no sense in the new language. They completely failed to separate the underlying meaning from the original vocabulary. An expert translator, however, does something entirely different. They first extract the pure, language-agnostic meaning of the story. They completely decouple the plot from the French language itself. Then, they take that pure meaning and reconstruct it from scratch using natural, culturally appropriate Japanese vocabulary. This is exactly, literally what Domain-MoT does. Just as a translator separates the plot from the vocabulary, DomainShuttle separates a subject's intrinsic features from its stylistic domain. It extracts the plot of the reference image, it discards the original language of its visual style, and it allows your text prompt to dictate the brand new language of the generated video.
Now, what's really fascinating about this slide is seeing how that exact translator analogy is actually engineered in the raw code. Let's dive deep into this diagram of the DomainShuttle architecture. I want you to trace the informational paths with me here. Take a look at the top left. We have two completely distinct inputs, the video pool and the ref image pool. In traditional older models, these inputs are just flattened out, concatenated together, and shoved through the exact same self-attention blocks. But look closely at what Domain-MoT does. After both inputs are processed through a frozen encoder and patchified into individual tokens, they enter the video DIT block. Notice the in-context self-attention module right there in the center. Do you see how there are two separate vertical columns inside it? The blue column is strictly handling the video features, and the orange column is handling the reference image features. They each have their own completely independent query, key, and value, or KKV projections. By giving the reference features a completely independent attention mapping pathway, the model is effectively disentangling them from the video features right out of the gate. The plot is officially separated from the language. But it actually goes much deeper than that. Look down at the bottom left, at that yellow oval labeled Domain-Aware ADLN. Now, ADLN stands for Adaptive Layer Normalization. Normally, layer normalization is just a tool to help stabilize training by normalizing the activations of the neural network. But adaptive layer norm shifts and scales those activations based on a specific conditioning signal. Here, the researchers introduce a domain-aware ADLN that is used exclusively for the reference branch. It takes the reference attribute embeddings, which are mathematically encoding the specific visual style, or the domain of the reference image, and it uses those embeddings to modulate the reference features. It's essentially telling the network, hey, listen, this reference image isn't just a generic array of pixels, it specifically belongs to the photographic domain or it belongs to the cartoon domain. This explicit mathematical domain modeling is the exact mechanism that allows the network to isolate the intrinsic identity from all that stylistic baggage. Finally, once it's clean, the decoupled reference features are injected back into the video branch via a gated addition, which you can see as that circle with a plus sign. This brilliant architecture is what guarantees that the reference identity guides the video generation without forcefully dragging its original visual style into the final output.
Moving on to Section 3, DualRoPE's Spatial Disentanglement. So at this point, we've successfully separated the identity from the visual style. That's huge. But we have another massive problem we have to solve when we try to generate videos with multiple subjects at the same time. Imagine you have a text-to-video model generating a video of a man and a woman walking together in a park. The model needs to know exactly, down to the pixel, where the man goes and where the woman goes. If the model gets even a little bit confused about spatial positioning, the characters start to blend into each other. The man might end up rendering with the woman's hair, or their clothes might suddenly swap colors halfway through the video. This phenomenon is called subject bleeding, and it has been a huge persistent issue in open domain video generation. To conceptually explain exactly how DomainShuttle solves this, I want to use another analogy. Let's call this the theater stage analogy. Imagine a large theater production. You have actors physically standing on a stage. Their exact physical positions matter immensely. If an actor stands in the wrong spot, they might block a spotlight, or they might physically run into another actor during a scene. This physical stage represents our generated video, and the strict coordinate system used to track where everyone is standing is absolutely crucial. Now imagine the characters' biographies, their deep backstories, their intrinsic identities, are all kept backstage in a filing cabinet in the director's office. Let me ask you, do those character biographies need to be assigned physical stage coordinates? Of course not. If you try to assign a strict X and Y stage coordinate to a piece of paper sitting in a filing cabinet, you are just going to create massive confusion. The biography of character A should simply be intrinsically, conceptually linked to the actor playing character A.
regardless of where that specific actor happens to walk on the stage. In the realm of neural networks, we use something called positional embeddings to tell the model exactly where tokens belong in a given space. Previous models made the critical error of applying the exact same positional coordinate system to both the video tokens, our actors on stage, and the reference image tokens, our biographies backstage. This profoundly confused the model, causing the identities to tangle and bleed together based on completely irrelevant spatial proximity. Let's return to our master architecture slide. But this time, I want you to focus purely on the bottom left subdiagram labeled B, Video Reference DualRoPE. This right here is the mathematically rigorous breakdown of that theater stage analogy we just talked about. Now, RoPE stands for Rotary Position Embedding. It's a highly effective, modern way of encoding positional information by mathematically rotating the token vectors inside the latent space. Notice the blue cubes in the diagram representing the target video tokens? They exist in a very clear 3D coordinate system: time, height, and width. This is our physical theater stage. Now, look closely at the green cubes representing the reference image tokens. They are not placed inside that 3D video grid. Instead, DomainShuttle takes them and assigns them to a completely separate, entirely independent RoPE space. By utilizing this dual RoPE mechanism, the model creates an explicit, hard separation in the latent space. Within that green reference space, different subjects, like, say, an image of a dog and an image of a cat, are kept mathematically isolated from one another, which completely prevents them from bleeding together. But representations of the same subject are actively pulled closer together. What this means in practice is that the model can fetch the intrinsic identity of the dog from that isolated offstage reference space and perfectly project it onto the precise physical coordinates of the dog in the video space, without the dog's identity ever accidentally bleeding onto the cat. It is a wildly brilliant, elegant solution to achieving multi-subject spatial control. All right, section 4, cross-pair consistent loss. Okay, so we have our decoupled architecture built, and we have our spatial disentanglement sorted out. But here's the reality of machine learning. An architecture is completely useless without the right training strategy to back it up. When we actually train this model, we need a way to mathematically force the network to prioritize the intrinsic identity over all those irrelevant environmental variables. Because even with domain monicity in place, the neural network might still be lazy. It might be tempted to look at a reference image of a man sitting in a dark red room and lazily assume that dark red lighting is somehow part of his intrinsic identity. We have to essentially beat that assumption out of the model during the training phase. Here is our final analogy to make this training concept intuitive. Think of a police sketch artist. Imagine a sketch artist trying to accurately draw a suspect. If you only give that artist one single photograph of the suspect, and let's say that photograph was taken under a harsh neon green street lamp from a really high distorted angle, the artist is going to struggle. They might end up drawing a person with an oddly shaped, elongated head and green-tinted skin. They simply can't separate the intrinsic physical traits from the severe environmental noise of that one photo. But if you give that exact same sketch artist 5 different photographs of the suspect, maybe one taken in bright, clear daylight, one taken inside a softly lit cafe, one taken from a low angle, and one taken with a harsh camera flash, the artist's brain does something remarkable. It triangulates. It observes all the variations across the photos. It actively ignores the changing environmental features like the lighting and the composition, and it deduces the unchangeable, true bone structure of the face. This is exactly the role of the crosspair consistent loss. It provides the neural network with multiple varying reference images of the exact same subject, forcing the model to deduce what is truly intrinsic and what is just redundant stylistic noise. Let's look at the pure PhD-level mathematics of how this is actually achieved in the system. This right here is the crosspair consistent loss formula, which is denoted as L subscript C. The crucial point here is understanding exactly what these variables represent in the training loop. We have an L2 norm squared. You can see that as the double vertical lines with the 2's on the outside. And this is measuring the exact mathematical distance between 2 different network outputs in the latent space. Our goal during training is to force this distance to be as close to absolute zero as physically possible. Let's break down the 2 terms inside those bars. On the left side, we have g theta of zt, t, ct, cr. G theta is our live trainable video generation branch. It is actively trying to generate a video starting from latent noise, ZT, at a specific time step T, guided by a text prompt CT, and conditioned on a specific set of reference image features, which we call CR. Now look at the right side. We have G star theta of ZT, T, CT, C star R. G star theta is a frozen copy of the network. It uses the exact same starting noise, the exact same time step, and the exact same text prompt. But I want you to notice that very last variable, C star R. This is an entirely different set of reference image features for the exact same subject. So what's happening here?
We have the exact same person, but two different reference images. Maybe one image is under a green streetlight and the other is in a bright cafe. We pass one image through the trainable branch, and we pass the other image through the frozen branch. The L2 norm mathematically forces the trainable branch to produce the exact same latent output as the frozen branch, despite having a completely different reference image as its starting point. To successfully satisfy this equation, the network has absolutely no choice but to ignore the lighting, ignore the background, and ignore the visual style of the reference images. It is ruthlessly forced to extract only the pure intrinsic identity, that true bone structure, because that is literally the only data that remains consistent across both CR and C*R. This specific loss function is the mathematical secret sauce that makes the visual style decoupling actually work in practice.
Section 5, Datasets and the rigorous training pipeline. So we've covered the complex theory and the underlying math. But as anyone who works in AI research knows all too well, a model is only ever as good as its training pipeline. You can have the most elegant, perfectly mathematically sound architecture in the entire world, but if you feed it garbage data, it is going to output garbage videos. It's that simple. Transitioning over to the data side of DomainShuttle, the researchers at HKUST faced a genuinely massive hurdle. To train a model to handle open domain multi-subject generation, you need an unprecedented amount of high-quality data that shows the exact same subjects across different visual domains. Let's thoroughly unpack this table, which details the 750,000 sample, high-quality dataset they painstakingly assembled for this project. Starting at the top row, we see image datasets like UNO, Echo40, and Musar, totaling around 200,000 samples. This data is what instills the base model with its basic personalization capabilities. But the real magic happens in the video modality. They utilized datasets called Phantom Data and OpenS2V, totaling nearly 700,000 videos. But here's the catch. Raw video isn't enough on its own. To make that crosspair consistent loss work like we just discussed, they had to build highly accurate reference image sets for these videos. So they built an incredibly rigorous filtering pipeline. They used grounding Deno to precisely detect objects within the frames, and then they used SAM2, the Segment Anything model, for multi-frame segmentation to perfectly isolate the subjects from the backgrounds. They even went a step further and ran visual semantic alignment via multi-model large language models just to throw out any blurred or semantically mismatched subjects. It's an incredibly clean dataset. But I really want to draw your attention to the bottom row here, Ditto 1M. This is specifically a video editing dataset where you have an original video and an edited version of that video in a completely different domain, say a real-life video that has been turned into a 2D anime style. Notice that they only used 50,000 samples from this entire dataset. Why so few? Why does this highly relevant edited video data account for only 3.3% of their total training data? The researchers offer a brilliant critical insight here. They explicitly restrict this edited data strictly to cross-domain augmentation, rather than using it for main supervision. Their reasoning is that if you train a foundation model too heavily on synthetic edited videos, the model actually begins to learn the weird artifacts and glitches of the editing process itself, which severely degrades the overall video generation quality. By using it purely as a tiny 3.3% augmentation, they teach the model the abstract concept of crossing visual domains without accidentally poisoning the foundational, realistic quality of the video output. It is a highly delicate, perfectly balanced training dial. Which brings us to Section 6, Results and Critical Discussion. We've seen the architecture, we've broken down the loss functions, and we've analyzed the training pipeline. Now we transition into the falling action of our explainer. It's time to actually look at the empirical success of DomainShuttle, evaluate the hard numbers, and rigorously critique its boundaries. The researchers built DomainShuttle on top of both the WAN 2.1 and WAN 2.2 base models, which, as you likely know, are absolute state-of-the-art video diffusion models in their own right. They benchmarked their new architecture against existing SDV methods across a grueling battery of both in-domain and cross-domain test sets, and honestly, the results are staggering. I really want to emphasize this massive number on the screen. DomainShuttle achieved an 18.7% improvement in the cross-domain score over the current state-of-the-art methods. To put that into perspective, in the world of cutting-edge AI research, an improvement of just 2 or 3% is usually enough to get a paper published at a major conference. A 5% improvement is considered a major headline-making leap. An 18.7% improvement? That is not just an incremental update. It is the definitive, undeniable proof of the decoupling revolution's efficacy. It proves mathematically exactly what we saw visually in that very first grid. This model can shuttle a core identity into a completely new visual style, like taking a real photograph of a person and putting them in a low-poly 3D world, almost 20% better than the absolute best existing technology on the market today. It's a game changer for visual style transfer. Now, to prove exactly why they got that massive 18.7% bump, they conducted ablation studies.
If you aren't familiar, an ablation study is where you take a highly complex system and systematically remove or disable certain components to see exactly how much each individual part contributes to the overall success of the model. Let's analyze this table line by line. The top line represents the naive method, which is basically treating reference tokens and video tokens exactly the same, like older models do. We can see the text controllability, measured by the JAMI score, sits at 0.664, and the cross-domain subject consistency is at 0.697. Now, when they add just the dual self-attention, meaning giving the reference and video features those separate attention paths we discussed, both scores tick up slightly. But look closely at the bottom line. When they add the full Domain-MoT module, which crucially includes that domain-aware ADA-LN we spend so much time on, the scores absolutely explode. Text controllability jumps to 0.687, and the cross-domain consistency spikes massively to 0.783. This data proves conclusively that explicitly, mathematically telling the network what visual style the reference image belongs to is the absolute key to unlocking true cross-domain generation. But let's have a critical discussion here. Is this model totally perfect? No, of course not. The researchers themselves acknowledge certain limitations. By designing these completely independent information processing paths for the video and reference branches, DomainShuttle is inherently computationally heavier than naive methods. You are essentially forcing the system to run parallel attention mechanisms, which inherently require significantly more VRAM and raw compute power during both training and inference. Furthermore, the model's ultimate success heavily relies on the quality of that SAM2 segmentation in the training pipeline. If the segmentation pipeline feeds the model poorly isolated subjects, that cross-pair consistent loss we talked about will inevitably learn the wrong intrinsic features. For real-world follow-up experiments, I would absolutely love to see this architecture push toward real-time inference optimization. And beyond that, I really want to see how this framework handles highly complex physics-based interactions between a real-world subject and a fantastic subject. For example, can a photorealistic hand hold a 2D cartoon sword, complete with accurate lighting reflections bouncing between the two different visual styles? That, in my opinion, is the true next frontier for open domain video AI.
Well, we have covered an immense amount of ground today, diving deep into the math, the architecture, and the theory behind this incredible paper. Let's take a second to consolidate this intensely detailed lecture into 3 distinct, memorable takeaways, summarizing this massive transition from copy-paste AI to true stylistic adaptation. First, feature decoupling via Domain-MoT. Remember the translator analogy? By giving reference images their very own attention pathway and utilizing domain-aware ADA-LN, the model brilliantly separates the plot of an identity from the language of its visual style. Second, spatial disentanglement via DualRoPE. Think of the theater stage. By placing the reference identities in a completely separate mathematical coordinate system from the generated video stage, the model actively prevents multiple subjects from bleeding into one another. And third, intrinsic extraction via cross-pair consistent loss. The sketch artist. By mathematically forcing the network to produce identical latent representations from differently lit and styled reference images of the exact same subject, the model learns to ignore environmental noise and capture only the true intrinsic bone structure. These 3 pillars working together create DomainShuttle, fundamentally mastering the art of open domain video AI.
The long-term implications of this research are genuinely staggering to think about. We are rapidly moving toward a future of AI filmmaking, where a director can simply cast a real-world actor, drop their reference image into a model, and flawlessly generate them inside a neon cyberpunk anime, a flowing watercolor dreamscape, or a hyper-realistic space station with absolute consistency and zero identity loss. The decoupling revolution has well and truly arrived, and it is going to change visual storytelling forever. Thank you so much for joining me for this graduate-level deep dive today on Gradient Daily. If you value this level of rigorous technical explanation, please smash the like button. It really, truly helps the algorithm know that there is an audience out there for deep, uncompromised learning. And be sure to subscribe and turn on those notifications so you don't miss tomorrow's explainer, where we will unpack another cutting-edge paper pushing the boundaries of what is possible in AI. Until then, keep learning, keep building, and I will see you next time.